All right, here we go. So now we're recording. Okay. Yeah, but on the recording, apparently your names and your pictures don't show up, so that's you know, it'll keep things private for you. So the assignment. Oh yeah, next week there are no classes and no tutorials. This week you have your introductory tutorial to do that's due this Sunday, which is the 17th, so by 11 o'clock p.m. Okay, so that's basic housekeeping. Let me show you the assignment. Okay, so here it is. Let me get rid of my video. Yeah, so today's lecture cover all the remaining material. It should get most of it. If not, there'll be a little bit left to cover the 2 weeks from now, but you'll be able to do 80–90% of your assignment after this lecture. So this is the assignment. It's propositional logic, and the first question will be translating into English. And here we'll be translating from English into logic statements. That's question 2. Question 3 is simply reducing these logical expressions and evaluating if they are true or false. And then, so from 4 onwards is sort of some of the stuff we're going to cover today. So we're going to show that these expressions are equivalent using, or actually you're going to find an expression that's equivalent to this one, and then you're going to show that they're equivalent using a few different techniques. And yeah, so this is stuff that we're going to cover today. Similar are the assignments to the exam. You will get a practice quiz. So for each of your 4 quizzes, you'll get a practice quiz. So it's a bit challenging because the quizzes, I want to make them online because I don't, it's really hard to deliver them otherwise. So it'll probably be multiple choice quizzes or short answer, fill in the blank, that sort of thing. But you will get a practice quiz that it's very, very similar to the quiz that you'll be looking at. And in general, the practice quiz will be at least as hard as usually once I convert it to multiple choice, it becomes a little bit easier. But yeah, all the questions that you see on the practice quiz will be, you'll see a version of that question on the real quiz. So, okay. Yeah, so this is stuff we'll get to later. So let's just stop the share. So are there any questions before we go on? That was the housekeeping part. And if I can answer some questions right now, or we can continue with the lecture. All right. Joseph, you still have your hand up. Do you have a question or? No. Okay. All right, so let's get started on the lecture. So all right, so today we're going to talk about logical expression translation. That's sort of a very brief overview and not really the entire story, but it's good enough for a title. So again, my disclaimer, these are based on the slides of Dr. Robert Collier. So any mistakes that you find in them are mine, and anything that is done particularly well is probably the result of Dr. Robert Collier. So, all right. So last lecture we had an introduction to discrete math. We talked about what is discrete math. So it's math that operates on discrete data. Why do we need it? Is because computers operate on discrete data. Yes, you should have. Yes, this lecture is posted. So if you go to CU Learn, you can actually get these slides and then follow along on whatever device you're using and then annotate along. So I'm going to try and go a little bit slower than I did last time. I think I had a few a couple of complaints anyway. So if I go too fast, there's you can either mention it in the chat, or you can, I think there's these control buttons that you can use, and that tell me that I should go faster or slower, so you can sort of all chime in with that if I happen to go too fast. Okay, and then so yeah, and the last lecture we looked at some simple applications of discrete math. So what kind of problems we might be able to solve with them. And we saw there was, in particular, there was logic problems. And then we looked at propositional logic. So we looked at atomic propositions. So that's basically a statement such as "it is raining out," and that statement or assertion can have a value of true or false. So that's basically what a proposition is. And then you can build this propositional logic is a branch of mathematics, and you can build propositional logic expressions. So you can combine atomic propositions using different operators. So we have pen's not working. Yeah, so we have unary operators, binary operators, and we can use these to combine atomic propositions into more complicated logical expressions. And then we can use truth tables to show show all possible values of a particular logic expression, because in particular because any proposition can only take on the values of true or false. So there's a finite number of outcomes, and so even as we combine them into more complicated logical expressions, there's always a finite number of different ways that you can combine the values and to get some output. So you can express all of them using truth tables. And then we looked a little bit at English translations, how to convert from a logical proposition to English and back. So we're going to look at more of that today. We're going to start by looking at two more logical binary operators. So binary operator means it takes two logical expressions and combines them. So we're going to look at the exclusive OR operator and the implication operator. So the exclusive OR is somewhat simple. We're not going to spend too much time on it, but we will. It is important to touch on. The implication is, I mean, it's not that complicated in terms of logic. The truth table is, of course, as simple as any other truth table. It's a binary operator, but in terms of translating between English and logic, we're going to explain sort of the connection behind English and the logic math expressions as it applies to implication. And so we're going to look at the inverse, converse, contrapositive, biconditional, et cetera, and then we're going to look at how we establish logical equivalences. So in general, that's with the truth table, but you can also sort of transform one logical expression into another. Okay, so exclusive OR is, we discussed last lecture how OR in English can have two meanings. I like computers, or I need this credit. That means either one of those can be true, or they both can be true. However, there's another way we can use the word or in the sense that I can turn left or right at the intersection. So now I cannot choose both. So it's the same word, but it has two different meanings. And so the logical or is associated with the first version, so this little V. But what about the second version? Well, that's our what we just talked about. It's our exclusive OR operator, also known as exclusive disjunction of two propositions, and it is denoted A exclusive OR B using this little symbol here. Okay, so that should be fairly straightforward. So A exclusive OR B is true if either A or B is true, but not both of them. And otherwise, A or B, exclusive OR B is false. So again, we can show basically every possible combinations of values for A and B in our exclusive OR operator. So if we have true, exclusive OR true, well, A can be true or B can be true, but not both. So then that would mean this is false. And then if A is true and B is false, then this is of course true because we have either A is true or B is true. And if A is false and B is true, then again we have this as true. And if they're both false, then again that's false. So that's how you can express that operator using our truth table. And here's a nicer version of it. So, and again, we discussed this a little bit last class, but in English, the word or can be used for both of these. So you really have to pay attention to the context. So a flipped coin can land on heads or tails. You like computers or you need discredit. Those are two different meanings of the same word in terms of logic. So we have to be careful of the context when translating. Although we won't use much of exclusive disjunction in this class, but you should be aware of it. And even yeah, then there are other ways to express exclusive disjunction as well. So it's not that's another reason why we don't get back to it. Yeah, so here's a little cartoon, Boolean hair logic. So if we take A and B, if we AND them together, then the AND has hair only where both A and B have hair. If we OR them together, then this character here has hair everywhere that A and B have hair. And if we do the exclusive OR, then we have hair only where either A or B has it, but not both. So that's a nice little cartoon, another way to think of it. And if, yeah, if you wanted to do me, it would be not. So I have no hair, so there you go. All right, so that covers exclusive OR. Is there any questions on that? That should be fairly straightforward. I think we get the truth table. I think we get the translations. It's not that complicated. So let's talk about the implication of two propositions. So the implication of two propositions A and B is denoted with this A arrow B and is read aloud as A implies B. Is there a math expression on exclusive OR? I'm not sure what that means. So exclusive OR is this one, right? So that's sort of the math expression. Hopefully that answers your question. All right. So A implies B is this little arrow here. And we can also say if A then B. So this is quite common as well. A only if B is another way to express it, but so we'll get into that a little more. We'll explore all these different options a little more completely in a few slides. But A implies B is false only when A is true and B is false. Otherwise, A implies B is true. So that's so let's take a look at what this means. So the truth table is of course quite simple. True. Yeah, I don't know if that's so I'm not sure what you mean by that, Ben, but that might be well, let's continue, and then if you have this doesn't clear it up, then you can ask me a question again. So A implies B. We said there's only one case where it's true. So if A is true and B is true, then this is true. If A is true and B is false, so basically what we're saying is if A is true, then B must be true. So if we say if A is true, then B is true, then this obviously means our statement is false. If A is true, then B is true, but A is false, then these get true. So this is, and so we'll try and explain the reason behind that. This is the part that can sometimes be a little counterintuitive. The fact that if A is false, then we evaluate A implies B to true. But we'll look at some examples of, and hopefully that we'll get across the logic behind that. Okay, so there's a nice, neater idea, a nice, neater version of it. So P implies Q. Yeah, so P implies Q. P we call the antecedent, and Q is the consequent. And A implies B is probably the most difficult operator to reconcile with the English language. It's easy to mess up sort of from a logical standpoint, because it can almost seem counterintuitive at times. Because when A is false, what are we really saying? And we're really saying nothing. And that somehow means that the expression is true. So if we say if A, then B, we're concluding B if we are certain that A is true. What if A is false? So false, A is false, then this expression, if A, then B, asserts nothing. So I'm going to say, if it's raining, I'm going to carry my umbrella, but it's not raining. So then is what I said false? Well, not really. Just because it's not raining doesn't mean that what I said is false. So it could still be true. So we're going to look at some examples, and hopefully it'll make sense to you. So if A is false, then we assert nothing, and it must be considered true. So if it's not explicitly false, then we conclude true in the case of implication. It's a little bit strange that way. So here's an example. Hopefully this will help clear it up. So if you have a Canadian passport, then you are a Canadian citizen. So this is an implication. And let's think of it as if this is a law. So we're going to say, if you have a Canadian passport, then you are a Canadian citizen. That's a law. And you're breaking the law if we somehow make this not true. Okay, so let's find out the cases where we were breaking the law. So we're going to say that A represents you have a Canadian passport, and B represents that you are a Canadian citizen. And we'll examine all the pairs of truth values for these propositions and their meanings. So I'm going to ask, so you guys are chatting, that's great. You guys are clearing it up. I'm going to stop checking the chat because it's slowing me down here. If you have a question for me, I guess I'll ask that you raise your hand. So by all means, keep chatting, explain things to each other. That's great. But I'm going to wait for a hand raise before I stop the lecture again, because I keep checking back. Okay. So we're going to examine all the pairs of truth values and the propositions and look at their meanings. So you have a Canadian passport and you are a Canadian citizen. So A is true and B is true. Now our law, our proposition, our implication is if you have a Canadian passport, then you are a Canadian citizen. So if both of these things are true, then there's no problem. So when both are true, this statement is obviously true. That should be clear. So if you do not have a Canadian passport, but you are a Canadian citizen, so A is false and B is true, then our law is if you have a Canadian passport, then you are a Canadian citizen. So did we break the law here by this statement? I'm a Canadian citizen. I don't have to have a passport, right? I can be a Canadian citizen and not have a Canadian passport. That's okay. So I haven't broken any laws in this case. So that means, does the first statement mean that the second statement is false? Well, the answer to that is no. It can still be true that if you have a Canadian passport, then you are a Canadian citizen. There's nothing false about that. You do not have a Canadian passport and you are not a Canadian citizen. So the law is if you have a Canadian passport, then you must be a Canadian citizen. So again, have we broken any laws? Well, no. If I'm from another country other than Canada, and I don't have a Canadian passport, there's nothing wrong with that. I haven't broken any Canadian laws. So again, did the first statement mean that the second statement is false? No, it can still be true. So we haven't explicitly broken this law. You have a Canadian passport, but you are not a Canadian citizen. Okay, so this sounds like trouble. So if you have a Canadian passport, then you must be a Canadian citizen. That's our law. And now we're saying that I have a Canadian passport, but I'm not a Canadian citizen. So did the first statement mean the second statement is false? The answer is yes. These statements contradict each other. So this is the only condition where this implication is false, is if one or more people who have passports but are not Canadian citizens. So if A is true and B is false, then the statement is a lie. Okay, so does that make sense to everyone, or anybody have any questions? So when I ask for questions, feel free to chime in on the chat. Would it change, for example, if it was a UK passport? No, so a UK passport is fine. So we're only saying that if you have a Canadian passport, then you are a Canadian citizen. So if you have a UK passport, we're not saying anything about that at all. So yeah, that doesn't break our law, so to speak. Any other questions? Okay. Okay, so if A then B is one common way to represent this implication statement in English. Okay, but there are other equivalent statements as well as variations. So we can say if A then B is A implies B, it's the same thing. B if A, that's the same as A implies B, right? So what I've done basically is I've just sort of turned this sentence around if I put a comma here. So instead of saying if A then B, I'm just saying B if A. So the meaning is the same between these two, but I've just changed things around. And if I was better at grammar, I could explain that, but I'm not. So B only if A. So now the implication goes in reverse. So now we're saying B implies A. If I say B only if A, I'm saying B implies A, and we'll look at some examples of that as well. And there's also B if and only if A. Then the implication goes both ways. So this arrow runs from A to B and from B to A, right? And that's yeah, that's basically A implies B and B implies A. So let's look at some examples. So I will eat something if there is salt on it. So that's this version here, B if A. And what we said is that means A implies B. So I will eat something if there is salt on it. That means there is salt on it implies that I will eat it. Okay. So the meaning of I will eat something if there is salt on it is anything that has salt on it, I'm going to eat it. All right. Logically equivalent to if there is salt on something, then I'll eat it. Okay. So is that sort of clear, or any questions? It may take some time before you get used to these. I still have to sometimes pause and think about all the different variations and what exactly we're saying. So yeah, if you find it a little bit befuddling, that's all right. That's perfectly natural. I will eat something only if there is salt on it. So the implication for this one, I will eat it, implies there is salt on it, right? So anything I ate would have had salt on it. So if I ate something, logically equivalent to if I will eat something, then there must have been salt on it. Okay. So yeah, hopefully that makes some sense. So here's another example. Suppose the only thing that could cause me to cancel class was illness. So I'm sick. So how would this be phrased as an implication statement? Starting with the form if A then B, since this is sort of the simplest way to express it in English, which of the following is true? So A, if I canceled the class, then I was sick, or B, if I was sick, then I canceled the class. So you guys can maybe chime in the chat, A or B. So which do you think? Definitely C, yeah. All right. So let's think about it. A couple of A's, yeah. A, I think. So we got a lot of A's. Can be both. So I'm saying that the only thing that could cause me to cancel class was illness. So let's think about what this means. So if I cancel class, then I was sick. Does that sort of follow from this statement? Or if I was sick, then I canceled class. So I said the only thing that caused me to cancel class was illness, but maybe is it possible that I could be sick and I didn't cancel class? So it could be that this one might be false. So yeah, the correct answer is actually A. Yeah, exactly. If I was a little bit sick, I might not cancel it. But if I got really sick, then I would cancel it. But I wouldn't cancel it for any other reason. So if I canceled class, then I must have been sick. All right, excellent. So yeah, many of you are catching on. This could also be translated as I canceled class only if I was sick. And I was sick if I canceled class. And that's really just sort of just shifting the if-then sentence around. All right, so if the atomic propositions were P, I canceled class, and Q is I was sick, then P implies Q, if P then Q, P only if Q, and Q if P are all equivalent. So let's consider the implication P implies Q. The inverse is, these are different sort of variations on the implication. So if I say that I have the implication statement P implies Q, then not P implies not Q is called the inverse of that implication. If I instead go from P implies Q to Q implies P, then I've written the converse of P implies Q. And if I do both of those things, if I invert it and convert it, so now I have not Q implies not P, then that's the contrapositive. So which of these, if any, is logically equivalent to P implies Q? And how could we find out? So yeah, feel free to chime in the chat if you have an idea. How could we find out is, and what do we mean by equivalent? So what we mean is that the expression for the same values of P and Q will evaluate to the same true or false value every time, or for every possible value of P and Q. So that's what we mean by equivalent. So what we can do is we can put all these in a truth table and see which of their columns are the same. So we have our P and Q lined up here. So then our not P and not Q are simply the opposites of those. And now P implies Q. So that's false only if P is true and Q is false. And now we want to see which of these. So here we have, this is the inverse, converse, and the contrapositive. We want to see which of these, if any of them, are equivalent to P implies Q. So not P implies not Q. Well, if not P is false, then of course these are true. And if they're both true, then that's true. But if not P is true and not Q is false, then this must be false. So we can see that this column and this column are not the same, since the F is in a different location. So these two expressions are not logically equivalent. So for an implication, the inverse is not the same as the implication itself. So let's look at the converse. So Q implies P, that's only going to be false. Sorry, not here. It's only going to be false when Q is true and P is false. Let's get rid of that. Yeah, so that's not the same. Again, if we look at this column and this column, that's not the same as P implies Q. Although you may have noticed that it is the same as not P implies not Q. Finally, not Q implies not P. So we're looking here, not Q is true and not P is false. So this is the only one that's false. The rest are all true. And we can see that actually these two columns are the same. So as it turns out, the contrapositive is both inverted and converted, and it's the only one that's equivalent to the implication statement, P implies Q. So this and this are logically equivalent. So the biconditional of two propositions is denoted A with this double arrow B, and it's read as B if and only if A, or you can say A if and only if B. Either of those is fine. They mean the same. So A if and only if B has a value of false when either A or B, but not both, have a value of true. Otherwise, A if and only if B has a value of true. So it has a value of true if A and B have the same value. So if both A and B are true, then A if and only if B is also true. And if both A and B are false, then A if and only if B is true. When it makes sort of sense, we'll go into a little more detail with some of these examples, but it'll make sense once we break it down into A implies B and B implies A. So yeah, if these are both the same, then we mark down true in our truth table. If either one is false, we say false. And if they're both false, then it's true as well. Okay, questions or everybody following so far? All right. And yeah, so I will eat something if and only if there is salt on it. So that works out too. I will eat something if there is salt on it. So if a thing has salt on it, I will definitely eat it. And if I ate something, then it definitely had salt on it. So that's sort of the English equivalent to that. And since things weren't confusing enough yet, there's other ways to express it as well. So we can use necessity and sufficiency to communicate implication as well. Although we don't use these versions of the word, we use, well, first, if we have two propositions N and S, so N if S and S implies N, and if S then N are all logically equivalent. And those are also equivalent to N is a necessary condition for S, and S is a sufficient condition for N. Right, so N is a necessary condition for S. So if S is true, then it's necessary that N is true. So you can think about it sort of like that. And S is sufficient condition for N. Well, that's basically if S is true, then it's sufficient that N is true. So yeah, so there's a lot of ways we can express implication in English. And here are a couple more to keep you on your toes. All right, so let's look at some examples. So we're going through this much faster. All right, I tried to slow down and was not successful. Okay, so we're going to translate this assertion to a logical expression. So we have, if it is raining in the morning, then I will wear my hat and my coat when I leave for work. So first of all, we want to take this assertion and break it down into a logical expression. So we want to find out the atomic propositions and we want to find out the logical operators. So what we do is we look for these keywords. So we know that if then is one way to express an implication. And we know that and corresponds to the logical operator and. So then maybe I break it down into it is raining is R, the proposition R. I will wear my hat is the proposition H, and I will wear my coat is the proposition C. And I found these atomic propositions basically by scanning for the keywords and then breaking it down around them. since I know how these things are structured, I can take out the atomic propositions. And then, yeah, so now we want to express this as a logical expression. So we're going to say, if it is raining, if A, then B. So that's sort of R implies whatever this entire proposition is, and then we can break that proposition down further around this and keyword. So R implies H and C. So if it is raining, then I will wear my hat and I will wear my coat. So that's how we can take an English expression and break it down into a logical expression. All right. So now let's look at how we can express that using a truth table. So here is, I mean, we're using a truth table. We don't necessarily have to, but we want to somehow show you every possible value of this expression. And so a truth table is one way to do that, and we'll look at another way shortly. But for now, here's all the possible combinations of R, H, and C. And from here, we can say, well, we want to break down. So we want to break it down into something simple. So we're going to, first, we're going to look at this sub-expression, and we're going to find the truth values for that. So H and C. So if we look at if we remember our logical AND operator, then H, both of the propositions have to be true in order for the AND operator to be true. So here it's true, but here C is false, so we get false. Here H is false, so we get false. Here they're both false. Here it's true, false, false, false. So yeah, we figured out this sub-expression, and now we want to figure out the entire expression. So we're going to look at the value here for R and the value here. So R implies H and C. If they're both true, then we can safely say that's true. Here we have R is true and H and C is false. So that's going to be a false. Here it's true, here it's false. That's again false. True, false. It's again false. I'm making those look like E's, but and here R is always false. And so if we recall implication, that means that these are all true. And let's hope I got that right. Okay, so now we've expressed all the possible values of this this English expression. We've changed it to a logical expression, and then we've enumerated all the possible values that it can take on. So here, obviously, if everything is true, then this expression evaluates to true. So it is raining, and I did wear my hat, and I did wear my coat. So then it's true. But if it rains and I do not wear the coat and hat, I was lying. So here, here I didn't wear my coat. Here I didn't wear my hat. And here I didn't wear either my coat or my hat, and it was raining. So my assertion that if it was raining in the morning, then I'll wear my hat and my coat when I leave for work is false. I lied when I said that. But if it doesn't rain, then I can wear the coat and hat or not. It doesn't matter. Or I can wear both of them. I can wear one or the other, or I can not wear either of them. But I haven't made this implication false. So that's sort of the explanation behind all of that. So, all right. Any questions? Is everybody following? Okay. So we're going to translate another assertion into a logical expression. Regular attendance of the lectures is necessary for passing this course. So first of all, we have to break this down into sort of a logical expression. And again, we want to do it by recognizing the keywords that represent logical operators and sort of taking them out and figuring out what the atomic propositions So here you recall is necessary. That has a meaning and implication. So we can break down our propositions around this keyword is necessary. So A is you attend the lectures and P is you pass the course. Okay. So regular attendance of the lectures is necessary for passing the course. And that is, so passing the course implies that I did regularly attend the lectures. Because if I didn't attend the lectures, then I could not have passed the course. So if this is false, I didn't attend, then P also has to be false for this to evaluate to true. All right. Yeah, and then we can fill in this truth table here. So here I've attended, I've passed the course and I attended all the lectures, so that's fine. Here I've passed the course, but I didn't attend all the lectures, so that's false. And here I didn't pass the course, so maybe I attended the lectures and maybe I didn't, but it doesn't matter. So if I passed the course, I must have attended, but if I didn't pass, then I may or may not have attended. It doesn't matter. So if I didn't pass here, then either of these, this can be either true or false, it doesn't matter. Regular attendance of the lectures is sufficient for passing the course. So this is another implication, but now it's in reverse. So what I'm saying is that if I attended all the lectures, then I have passed the course. So attendance is sufficient. So again, this is true, false, true, true. So if I didn't attend the lectures, maybe I passed the course, maybe I didn't. But if I did attend the lectures, then I must have passed the course. If I didn't pass the course, then I've lied with this statement. So that's why we get the false here. So if you attended, you passed the course, but if you did not attend, you may or may not have passed. All right. So that's that set of slides. Is there any questions? Okay, so before we start the next one, no, maybe I'll start the next one, I think. Speed run, yeah. Yeah, I'll try and hit your little, there's these go faster and go slower buttons, so you can sort of chime in and remind me to go slower if you want. Yeah, so let's go to the next part. Oh, I hit the wrong one. Sorry, I'm just for some reason it's not for some reason the one I want's not showing up. Oh, here we go. Okay. Yeah, so it is a bit of a speed run, but you'll also have the video to go back and go through things. So hopefully that sort of balances out. So yeah, establishing logical equivalence. So again, the usual disclaimer, these are based on slides by Dr. Robert Collier, and if you find a mistake, then they're mine, and whatever is absolutely correctly done is probably his. So okay. So in logic, the set of possible values is finite. So what that means is that, of course, each of our variables takes on either true or false, each of our propositions. So the set of all possible values is finite, so we can always make a finite table for some expression. And expressions and corresponding English statements are equivalent if and only if their truth tables are identical. By identical, what we mean is that the final column of the truth table. So not the sub-expressions, we don't care about that necessarily, but the final column should match. And we saw that a little bit when we went over how P implies Q is logically equivalent to not Q implies not P. So an implication is logically equivalent to its contrapositive. So we consider the expressions. So let's go back to math for a second. So 2 times x plus 4 and 6 times x plus 2 over 3. So are these equivalent expressions? Well, it's difficult to say because x can take on any value. So you can probably evaluate it with a formal proof without too much difficulty and find out if they're the same or not. But there are, of course, more complex expressions where you can't do this, since x can take on every value. But if x can only be a value between 1 and 10, then you can just substitute in every different value for x and see if they evaluate to the same value. And you can put all that, say, in a table. So this is sort of a little bit of a review. Yeah, we already saw this, but let's go over it again. So this is any implication is true except for the one when the antecedent is true and the consequent is false. But if the antecedent is false, then it's always true. So we get true, false, true, true. And not P is just the opposite of all of these values. So we get false, false, true, true. And then not Q is the opposite of Q's values. So we get false, true, false, true. And then we can see that not Q implies not P. So that's, if not Q is false, then this must be true. And this is the only condition where this is false, and the rest are true. So yeah, we've established once again that P implies Q is logically equivalent to not Q implies not P. So an implication is logically equivalent to its contrapositive. So we can also prove other expressions are equivalent. So we'll take not P and not Q is equivalent to not P or Q. So again, we're going to fill out the truth table, but now we have to express, first we want to express one of these, and then we'll express the other. So we can fill this in. The opposite of true is false, true, false, true. So that's not Q, it's just simply the opposite value of Q. And then P and not Q, so both of these must be true, and it's not in this case, so it's false. Here, both these are true. Yeah, somebody raised their hand.
I remember you mentioned that you would have to show the steps on tests and whatnot. By
Yes.
that, like when making a truth table, you have to show the sub expressions, and you can't just go to the last one.
Correct.
So, like in the test, we have to show the sub expressions to prove following equivalence kind of idea.
So the tests, yes, ideally that would be the case. You'll definitely have to do that on assignments. The tests, it's a little more difficult to do that. So I might ask you for, I'll probably do something like this, and I'll ask you for the last column and then the number of sub expressions that you had to evaluate to get there, something like that. So it won't be exactly this, because it's difficult to administer a test, unless I have everybody take a picture with their phone of some piece of paper, but then you get a problem where some of it is, I've seen some atrocious photos like that where everything's in shadow and you can't tell what's there. So I don't want to do that. So yeah, definitely show every step on the assignment. It likely won't be an issue on the test, but I might ask you how many sub-expressions you had to evaluate.
Okay, thank you.
Yeah, it is important that you don't skip steps. One, because we want to see that you understand what you're doing. So showing every step shows that clearly, even though it can be sort of tedious. And yeah, it cuts down on just copying an answer, right? Okay. So P and not Q. So they're both true here, so it's true. We have false and false, which is false. So that's false. So then, and then we can evaluate sort of the negation of this expression. So we just simply take whatever is in this column and we take the opposite. So true here, false here, true here, true here. Okay, so now we've taken this expression and now we have all of the values associated with it. So now we want to evaluate this side. So first we need not P. So that's going to be false, false, true, true. And then not P or Q. So we take this Q, at least one of them is true, so this is true. Both are false here, so this is false. Both are true, this is true, and we have one true, so this is also true. So we've seen that, yeah, so we wanted to show that this expression was equivalent to this expression, and since they have the same column in the truth table, we've shown that that's true. Okay, 6:30, since we are doing a speed run, I think we'll take our break early. So we'll take a 10-minute break. Otherwise, I'm just going to run through everything before, you know, give you a chance to go to the bathroom or whatever. So we'll be back at 6:40. Okay, we're back. Yeah, I was just going to ask if anybody had any questions. Apparently somebody does. Should I put commas in my English expressions for the logical statements to make it more grammatically correct? We're not really marking grammar so much, so if you make small errors, that's fine. Yeah, as long as, as long as it makes sense, enough sense, then it should be fine. Okay, any other questions before we get back to the speed run? Alrighty. Okay, I'm gonna share my screen. All right, so we've shown by truth table how two expressions can be logically equivalent. Can we write but as A and not B if we want? Can we write but as A and not B if we want our atomic expression to be positive? So I'm not sure exactly what you mean by that, but yeah, you can. Well, your atomic, yeah, if you've expressed something negative, then your atomic expression should be the positive. Yeah. So I think, yeah, the answer would be yes, if I understood you correctly. Okay. All right, so we talked a little bit about P exclusive OR Q, so the exclusive OR operator. So we want to rewrite that using only the negation, the not, the logical AND, and the logical OR operators. And then we're going to prove that our solution is correct using truth tables. So how are we going to do this? So let's express sort of P exclusive OR Q in English. So in English, we would say either P or Q, but not both. So then now we have an English statement and we want to translate it into a logical expression. So we might say P or Q and not P and Q. And that's our best guess at the moment. So let's see if that's actually correct. Yeah, so we write up our truth table. So we know P exclusive OR Q. So if both P and Q are true, then this is false. But if only one of them is true, then it is true. And if both of them are false, then it's false. So now we figured out this expression. We have a column for it. So now let's figure out the next expression. So we're going to have to break it down into sub-expressions and then evaluate them and then put them together. So P or Q. So if either P or Q is true, then we write true. So in this case, P is true. In this case, Q is true. And the only one that is false is when both P and Q are false. Okay, so we have our first sub-expression, and now we want to evaluate our next sub-expression, which is this one. So we start with the expression without the negation. So P and Q, well, that's only true if both of them are true. So in this case, it's true. In all the other cases, there's at least one false. So this must be false. And then the negation of P and Q is simply whatever value we have here, the opposite. So we have false, true, true, and true. And now we want to take this guy and apply the logical AND operator with the values in this column. So we have true and false, that's false. True and true, that's true. True and true, that's true. And false and true, that's false. And so if we look back at our P exclusive OR Q, then we have false, true, true, false, and that's the same as this. So we've proven that these two expressions are logically equivalent. So we've taken P exclusive OR Q, we've said what we think it means in English, and then we've translated that English into a logical expression, and it turns out that that was correct. Okay. So before we get here, is there any questions on this stuff? Okay. So the final column of a truth table can be used to categorize an expression. So these are important categories. So a tautology is an expression that is always true. So if you look at the final column of your truth table, it has all true values. A contradiction is an expression that is always false. So if we look at the final column of our truth table, it's all false values, and every other expression is a contingency. So if there's some combination of true and false in our final column, then we say that that expression is a contingency. So these are, we can classify them by using a truth table. So we write out the truth table and we look at the final column and we can easily classify them. So for this next exercise, we're going to demonstrate that this P implies P or Q is a tautology. And then we're going to demonstrate that P if and only if Q and not P and not Q is a contradiction. Can this be explained with Venn diagrams? Venn diagrams are more for sets. So no. There might be a way to do it, but generally speaking, that's not what we use Venn diagrams for. Of course, you can, in math, you can sort of define things to mean what you want. So as long as you're precise in your definition, you can basically do anything you want, but we will not be expressing these using Venn diagrams. So we'll use Venn diagrams when we get to sets. Okay, so we're going to demonstrate that P, any other questions? So we'll demonstrate that P implies P or Q is a tautology. So again, we have our truth table, and we break it down into our sub-expressions, so P or Q. So it's true as long as at least one of P or Q is true and false otherwise. And then so P implies P or Q. So if P is true and P or Q is true, then this is true. Again, P is true here, and this is true. So the antecedent and the consequent are both true, so it's true. Here, P is false, so no matter what we have in this column, this is going to be true. So now we've shown that P implies P or Q is a tautology because all of these values are true. So no matter what, this expression evaluates it true. No matter what values we supply for P and Q, this is always true. Okay, good. Questions? All right, so here's a little more complicated expression. So P if and only if Q and not P and Q. So again, we take our sub-expressions and we evaluate them. So as long as P and Q are both true or both false, that will be true. So we have true here. If they have different values, then it's false. And if they have the same value, even if it's false, then it's true. So not P takes on the opposite values of P. And then not P and Q, so we look at, well, if one of them is false, then this must be false. So not P is false for both of these. And then here, we can see not P and Q is true. And here we have Q is false, so this is false. So now we want to combine this expression and this expression using our logical AND. So they both must be true, but here we have at least one false. Here we have both false, so this is false. Here we have P if and only if Q is false, and here we have not P and Q is false. So we've shown that P if and only if Q and not P and Q is a contradiction. So no matter what values we supply for P and Q, this expression will always give us a value of false. All right, so a fundamental property of equivalence is transitivity. So if two logical expressions are equal, and one of them is equal to a third, then the first one is also equal to the third. So if A equals B and B equals C, then A equals C. That's transitivity. So that's common in math, of course, and it's also true in logic. So we can use this transitivity property along with some well-known logical equivalences to transform one expression into another equivalent expression. Okay, so this can be an alternative to truth tables for proving equivalence. So we're gonna look at some of these rules, and we're gonna look at how we can apply them. So here we have what's called the identity rule. So if we have a proposition P and true, then it's always equal to P. So we can, in a sense, look at the truth table for this. If we have true and false, and then in this column we have P and true. So we have true and true, which is equal to true, and we have true and false, which is equal to false. So P and true is logically equivalent to P, right? Will we get formula sheets for these logical equivalences on a test? Yes. On assignments, you can refer back to the notes. Oh, let me think actually. Maybe not the quizzes, but on the final exam, I think we give you those. I'll have to actually check back. Yeah, some of these are difficult to memorize, and there's quite a few of them. I think we. Anyway, I'll get back to you on that. So in Q, or false is equal to Q. So yeah, if Q is true, then true or false is equal to true. So Q, true, false, Q or false. So yeah, if Q is true, then Q or false is equal to true. And if Q is false, then Q or false is equal to false. So these are logically equivalent expressions as well. So that's identity. Idempotent means that if I and something with itself, so P and P is equal to P, and Q or Q is equal to Q. So if I and something with itself or something with itself, it just takes on its own value. So domination. So up here, the identity, we saw how just using true and false really didn't change anything. But here, if we have a true or false value, it actually dominates the expression, because in this case, true or anything is always equal to true. And in this case, false and anything is always equal to false. So we call that domination. So these are all little things that you can use to help transform one expression into another. And there's more. So these are quite simple. So P and Q is equivalent to Q and P P or Q is equivalent to Q or P. So we can change the order of them and it doesn't affect anything. And we call that the commutative property. And this, you may remember these properties from math. And the associative property is that if I have P and Q and R, it doesn't matter if I do P and Q first or Q and R first, they will logically be the same. So if I put my brackets to enforce the order of operations, it doesn't really matter where I put them, as long as all of these operators are the same. So they're either all and operators or they're all or operators. So, and if that's the case, then we can put our brackets wherever we want. And yeah, good. Is this question so far? Is everyone following? Okay. Distributive. So this is if we have an order of operations here, we have the and inside the brackets, and we have an or outside the brackets, then we can, in a sense, distribute this P over the Q and the R. So we have P or Q and R is logically equivalent to P or Q and P or R. And by the same token, if we reverse these operators, put an and here and an or in the brackets, we can distribute them as well. So we have P and Q or R is equal to P and Q or P and R. And you can think of it as similar to distributing multiplication over an expression that's in brackets, right? So if I take 3 times 4 plus 5, that is equal to 3 times 4 plus 3 times 5. So I've distributed that 3 over the 4 and the 5. There's more. Negation. So P and not P is false. So if I have P and not P, then I have true and false, or I have false and true, and both of those evaluate to false. On the other hand, P or not P is equal to true, because at least one of those values must be true. And so we call that rule negation. Absorption. So this is an interesting one. It's not as sort of intuitive as some of them. So if I have P and P or Q, that's equal to P. And if I have P or P and Q, that is also equal to P. So the Q, in a sense, doesn't matter. And we call that absorption. And these, if you're not convinced, you can always run through the truth table on them and convince yourself. And of course, double negation is, so somebody's mentioning these other symbols. So the curved symbols like this, these are for set operations. So they're very, very similar. So we're going to see them a few lectures from now. And logically, you're going to see a lot of similarities between propositional logic and these set operations. But no, they're not the same. So they're similar, but they are for sets, and you'll see a lot of similarities, but they're not the same. So you cannot use these interchangeably. All right. Any other questions? All right, no problem. All right, so double negation. So if we have not P, so we've changed the value, twice. We've changed it from true to false and then back to true, or from false to true and then back to false. So it's just equal to the original proposition. So that's called double negation. And there's more. Implication equivalence. So this is an interesting one. You'll probably use it quite often. If you want to transform one expression into another, you can't really do much with this implication, but you can with this. And if you can definitely roll out the truth table and convince yourself that they are equivalent. On the other hand, if we look at this, we know that if P is false, if P is equal to false, then this is always true. So if P is equal to false, then not P is equal to true, and true or anything is always true. Oops. So in a sense, if you really want to get down to the base of it, you can write out the truth table, but otherwise, just remember that if P is false, then it's always true. Biconditional equivalence. So P, if and only if Q, well, it should not be any surprise. Quite literally, if we translate this to English and back to logic, say P implies Q and Q implies P. So that's if we take the if and the only if at the same time. So that's called biconditional equivalence. Yeah, and then De Morgan's law is another one that's sort of interesting because it's not always, I guess, maybe not as intuitive as some of the other ones. But if I have not P and Q, that's equal to not P or not Q. So I flip my operator from an and to an or, and I negate both of my operands. And this also works for not P or Q. So I flip, or I negate both of my operands and I flip my operator. And any of these can also work in reverse. So I can go from not P or not Q back to not P and Q in brackets. That's not a problem. Okay, so that's a lot to throw at you at once. And yeah, there's a lot that even I tend to get confused with, negation, identity, idempotent. They're all very similar, but so on your assignments, you'll be able to look them up. And I'll get back to you on the quizzes. But so we're going to work through some exercises now, but any questions on any of those? Yeah. Sure. I'll go slower. Okay, so we're going to demonstrate the logical equivalence of these two expressions. And we're going to transform the first expression into the second expression using the laws that we just seen. So we could also show this with truth tables. We could write these out into two truth tables and examine their last column and check to see if they're logically equivalent. And in general, if P is equivalent to Q, can we say that not P is equivalent to not Q without further proof? Yeah. Yeah, that's not a problem. Although in general, it's always safer to, state everything explicitly, but something exactly what you said here, if P is equivalent to Q, then can we say not P is equivalent to not Q? Absolutely. I think that should be pretty much a no-brainer. Okay, so we're going to translate. We're not going to use truth tables. We're going to use the laws. So let's take a look at it. So what we're going to do is we're going to translate not A or not A and B into the other one. So what we're going to do is try to do some pattern matching. We've seen all the laws, and now we want to say, well, which one can we apply here to change it? And you might ask, well, how do you know which law to apply? And that's very valid. And the answer is, generally speaking, it's sometimes not apparent, but you start to get a feel for it. So sometimes you're just going to have to work through an experiment, but other times it seems obvious. So let's try and pattern match this expression to one of our laws. So what if we let D equal, so the variable D, we're going to set it to not A and B. So this little sub expression here is going to become D. And now we have this not A or D. So now which rule does anybody know or anybody remember what we might apply here? So at this point, we're just we're taking shots in the dark. Implication, De Morgan. So implication equivalence. So we can apply De Morgan's. Implication equivalence would be if I had this with no brackets, then I could say that's equal to A implies D. Distribution. Yeah, you could distribute A over this. And then apply the negation operator. But you're going to see, yeah, we're going to eventually do distribution anyway. So it's just, you could have chosen to do it in a different order. Absolutely, you could have used distribution first. We're just going to do it this way. So we can match it. Yeah, is it better to work with the innermost expression first or from the outside towards the inside? Yeah, I don't know that there's a hard and fast rule for that. So maybe do what you're comfortable with. What's going to happen is that you're going to do the exercises in the assignments, and then you're going to start to get eventually, after you bang your head off the wall a few times and try and figure it out, you're going to all of a sudden have these eureka moments where you start to see these patterns, and then you can apply the rules more consistently. But at first, you just gotta kind of take a stab at something and then see where that takes you, and see if it takes you closer to the expression you're trying to get to or further away. But we'll go over, there's a few tricks we can use. So the one here that we're using right now is pattern matching, and we'll show you some other ones too. Okay, so not A or D matches De Morgan's law. So De Morgan's law is if we have not P or Q in brackets, that's equivalent to not P and not Q. So we can replace P with A and Q with D and apply De Morgan's law and get not A and this should be D. Oh no, sorry. So D is equivalent to this expression. So yeah. All right, so we take this original expression and we apply our De Morgan's law to it. And so we negate A and we negate this expression. This is our old D, so we get not A, and then we flip this operator, not A and not, not A and B. All right, so now we want to pattern match again. So we want to look at this and check with check our laws and see, well, what can we apply here? So we can't do distribution anymore because these are the same, and also you have to evaluate this negation first. But let's just look at this one. So we're just going to look at this sub-expression here. So again, we can pattern match this sub-expression to De Morgan's law. So De Morgan's law is not P and Q is equal to not P or not Q. So we can replace P by not A and Q by B, and then apply De Morgan's law. So we've gone from here to here. So we flipped this operator, and we've applied negation to not A and negation to B. All right, is everybody following? Questions? Okay, and then, yeah, well, spoiler alert, I should have asked you before advancing here, but so the next thing we could apply is, if we're pattern matching, we can apply this double negation law. So not A is equal to just plain old A. So what should we do next? And or what pattern can we see here that we could do next? And somebody mentioned it earlier. Yeah, so here we can distribute now. So let's see where that gets us. So when we distribute, we say A, not A and A is the first term, and or not A and not B. And that's, again, if this seems a little confusing, think back to how you distribute multiplication over addition in the example that we saw earlier. So now, what kind of patterns can we match? Does anybody want to take a stab? So I have this not A and A, right? Yeah. So yeah, the negation law. So we have not A and A gives us false. So false or anything gives us what? Anything, yeah. So false or anything gives us anything by the identity law. Well, okay. So first we use the commutative law. So I don't expect you can use the commutative law without declaring it. But yeah, I don't mind if you, yeah, to me, this step is extra. You don't need to do this. But yeah, the identity law. So false and anything is anything. And then, or false or anything is anything. So we've demonstrated the logical equivalence of these by transforming one into the other. Okay. So did everybody follow? Is there any step that anybody wants me to go over again? All right. Okay. So that's great. We've changed one expression to another. We've seen how to apply these laws, and it takes a little bit of. It does take a. Did you name every single law? Yes. You need to name every time you take a step. So two things that I should point out on an assignment. Don't double up on your steps. Make every single step. Do one step per line, and always name them. The only thing I don't mind if you combine steps with the commutative or the associative, because those are relatively simple. I don't really care about those. It's sort of clear what you have to do there. The other ones are sort of more significant steps. So I do want you to A, only do one step per line, and B, label that step. All right. So using truth tables, we can establish a tautology. That's all truth values, a contradiction, which is all false values, or a contingency. So given an expression, we write up a truth table, and we can tell you, or I could tell you by looking at that truth table, which one of these categories it falls under. But what if we're using equivalences? So equivalences are a little bit more difficult at first, but they can, once you get used to them, they can be easier than a truth table, which can get really large if your expression is large. So let's demonstrate that P implies P or Q is a tautology without using truth tables. So we're going to use logical equivalences and show that this is equivalent to true. So what's the first thing maybe that we want to do? What's the first step? So we have an implication. Those are difficult to work with. Yeah, so we want to use the implication equivalent and get rid of that implication. So this is equivalent to not P or Q. And now what do we do? So if you guys spot something, just shout it out in the chat. But let's examine this. We see that both of these use the logical OR operators. So we can easily move the brackets if we want. Since it's OR and OR, we can apply the associative law and move the brackets. And again, this is a step that you can skip in your assignment or test. And then I sort of jumped ahead of myself here and I gave it away. The next step, so not P or P, so true or false always evaluates to true by the negation law. And true or Q, does anybody remember what step we would take or what law we would apply? Domination, yeah. Well, commutative and the domination law. So true or anything is always true. It'll dominate your expression. So we've shown that P implies P or Q is logically equivalent to true, and thus it's a tautology. So no matter what values we supply for P and Q, this expression always evaluates to true. So you can show that using the truth table, or you can go through these steps. And these steps, at first, they're more difficult, but then once you get used to working with them, they're much, much easier. So demonstrate that. I don't think I'm going to go through this one. We can if you like, but it's a lot. Well, let's go through a couple steps, I guess. So we'll demonstrate that this is a contradiction without using truth tables. So here I have P if and only if Q, and I've jumped right into the first step here. So I've done the biconditional equivalence. So this P if and only if Q is logically equivalent to P implies Q and Q implies P, and then this part stays the same. And then I can do implication equivalence here. And so anytime you see an implication, you probably want to apply the implication equivalence. It's just easier to work with. So we apply it again here. So now instead of our two implications, we have not P or Q and not Q or P, and not P and Q. Now again, this is Yeah, so we can use associativity and commutativity. So I combine them into one step. Like I said, for these two, I don't mind you doing that. And I did this here in the interest of space. So what I did is I took these brackets away, and then since these are all and operators, I can move not P over here and Q over here, and it's still logically equivalent. So again, this is a little more complex than the last one. This might be something you have to go back to on your own and try and work through it to see everything that's going on. And then I can do, so here I have not P or Q and not P. So that's absorption. So then this goes away and we're left with not P. And then if we look here, we can do distribution. So we can distribute this Q. So we have not Q and Q or P and Q. So this, of course, is negation. It always evaluates the false, and then false or anything is identity, and then associativity and negation. So I move the brackets to the not P and P, which evaluates the false, and false and anything is false by domination. Okay, so that one's, I debated whether or not to include this one because it's a little more complicated than, but whatever. It's fine, you can always go back and revisit it later. Is there any questions on any of these steps or anything you want clarified? Okay. All right, so a logical expression that's a tautology can be shown to be equivalent to true, so that's great. And if a logical expression is a contradiction, it can be shown as equivalent to false. So we've shown you both of those. So how do we show contingency? So that's, I guess, the tricky part. Because if we can't reduce it to either simply true or false. So we're going to reduce it to some other expression. But how do we know that that expression can't be reduced any further? So that's the problem. So, and the solution is that we have a format for writing normalized or standardized expressions in logic. So we have, when all expressions share the same format, we can easily compare them and evaluate whether or not they're a contingency or not. And how we can do that is we model them off of the truth table. So, and what that's called is, so an expression is in disjunctive normal form if it's a disjunction of one or more conjunctions. So here's the form, conjunction. So remember, conjunction applies to logical and disjunction applies to logical or. So here we have a conjunction, a set of conjunctions that are, held together by disjunctions, let's say. So the only operators permitted are negation, which are inside the brackets. So we want to apply these brackets so that all the conjunctions are done first. Recall, so there is, there is sort of a standardized way to do it, but we always, in this class, we always apply the brackets. So we do the negation inside the brackets, conjunction inside the brackets, and the disjunction would be outside the brackets, binding those conjunctions together. So that's disjunctive normal form. If it's in full disjunctive normal form, each variable that you're working with appears exactly once per conjunction. So that looks like this. So we have an expression on the variables A, B, and C, and it's in full disjunctive normal form. Then we have any number of conjunctions that are joined together by disjunctions. and A, B, and C appear in each of them. So here we have A, B, and C. And here we have A, B, and C, but we have the negation in front of A and B. And here we have, of course, A, B, and C, but the negation is in front of B. So this is full disjunctive normal form. And this is sort of the standardized way to, or the canonical way to express these expressions. All right. Any questions? Is everyone following okay? All right. So you recall the expression earlier. So if it's raining, then when I leave for work, I wear my hat and my coat. So in full disjunctive normal form, we could express it like this. So we have 1, 2, 3, 4, 5 conjunctions, and they're all joined together by these disjunctions. And we can confirm that using the truth table. So here's the truth table based on this expression. So we've already done it all for you, so you don't have to. So how can we use the truth table to confirm this? So there's they're sort of outlined in blue, but does anybody, I guess, spot the pattern or why we could say that these are equivalent without just by looking at them? All right, so you might notice that these squares are outlined in blue, and that we have 5 true values in our final column, and we have 5 conjunctions. So each of the 5 truth table rows, each 5 truth, that's weird sentence, but each of the 5 truth table rows that evaluates to true corresponds to exactly 1 conjunctive clause. So let's take a look. So here you can see that R and H and C corresponds to this row in our truth table. And we'll see that, hey, it's because R is true, H is true, and C is true. If all of those are true, then this evaluates to true. So if all of them are true, then R and H and C evaluates to true. And then because it's or, this entire expression, true or anything is true by domination, right? So we can see that if we have a T in these columns, then that corresponds to just the variable itself. And here we can see another value of true, but we have R is false, H is true, and C is true. So we have the H and the C are here, and we also need this one to be true. So in order to make that proposition true, we negate it, right? So since R is false, we apply negation, and then it's true and true and true. So then this clause becomes true. This conjunction becomes true. All right. And essentially the pattern is if normative forms are not used. If you're asked to prove an expression is a tautology, a contradiction, or a contingency using expressions, then full disjunctive normal form is how you prove contingency. All right, so that's, yeah, you won't, and that's generally how these questions will go. So you will need to use full disjunctive normal form to prove it's a contingency, yes. Because, well, we'll discuss that. But basically, each of these conjunctions corresponds to 1 row in our truth table. So here we have false, true, false corresponds to not, regular, and not C. Okay, so can everybody see how this, any questions on this part, why these are equivalent? All right. So now, so we can see that it's equivalent using the truth table. And so we're going to get to the question in a minute. But first, we're going to convert this expression into its full disjunctive normal form without completing the truth table. Well, we're not going to do all of it. because it's really long, but we'll show you how you would do it. So the first step is the implication equivalence. So anytime you see an implication, you basically want to get rid of it so that you can start working with these things. Now you can distribute this, or you can do any number of things. Yeah. So implication equivalence is the first step, and now we want to introduce, so observe, first of all, that this is in disjunctive normal form, but not in full disjunctive normal form. So this is a conjunction, technically speaking, and this is a conjunction. So we have it in disjunctive normal form, but now we want to introduce, we want to put it into full disjunctive normal form, which means we want to get the R in here, and we want to get H and C over here. Yeah. And so, yeah, that's, well, that's what I explained there. So one way to introduce a new variable is by using identity. So we can introduce the true. So true and something is equivalent to, true and an expression is equivalent to the expression by the identity. And then we can use negation to introduce this R variable into this, this conjunction. And then, so we have R or not R, which is equivalent to true. And then we can distribute. So what we've done here is we've taken this proposition, this expression, and we've distributed it onto the not R and the R, right? So since this is an and this is an or, we can take this and distribute it and get R and H and C. So now we have a full disjunct or a full conjunction. And here we have not R and H and C. We have another full conjunction. So all three of the variables are represented, and they're separated by this disjunction. All right. So now we want to, how would we expand not R into the remaining clauses for full disjunctive normal form? Well, basically we follow this pattern: identity, negation, and distribution. Right. So if we have not R, we use identity to introduce a true. We can use negation to introduce H or not H, and then distribution to put it into disjunctive normal form. Okay, so here we've distributed the R among the H and the not H. And then we can add C and not C to both sides using the same series of steps. So identity, negation, distribution to introduce new variables into your conjunctions. And then at the end, you might find, so this gets really long, as we saw, it's 5 conjunctions, and some of them might be repeated, and we can use commutativity and idempotent to eliminate the repeated. All right. Any questions on this? And yeah, there are alternative ways of doing this. So you could try, although I didn't try it, you could try, no, if you distribute that, then actually that's no good, because you end up with not R or H and not R or C, which is kind of the opposite of what you want. So now you have the disjunction inside the brackets and the conjunction outside. All right. Generally speaking, you insert a true. Yeah, that's how it's going to. You basically follow the steps. And I already forget them. But identity, negation, distribution. Yeah, so you want to insert the true because the true comes with this and. and it's the and that you want. So once you convert it using negation and then distribute it, you end up with these conjunctions joined by the disjunction. So if you try to use, so you could also do this is equivalent to or false, but now you're going to end up with the disjunction inside the brackets, which is what you don't want. So yeah, in order to go to full disjunctive normal form, you kind of want to follow this pattern. Identity with true, and then negation to introduce one of the variables, and then distribution to get it into disjunctive normal form. Okay. Any other questions? All right, so every logical expression can be converted into one and only one up to commutativity. So we can change the order of our conjunctions, but we don't change the we don't change the composition of them. So they're still composed of the same elements, but we could change the order around. That's fine. All right. So we have one way to express it in full disjunctive normal form, and that is you're going to have a conjunction for each of the rows of your truth table. So we can use this to demonstrate that an expression is a contingency. So how do we do that? Is anybody following and want to take a stab at it? What is it about full disjunctive normal form that can tell us that it's a contingency? All right, I'm not sure what that means. Could be correct. Can you tell if there's a case missing for it to always be true, to be always true? Yeah, that's, I think what you said is what you do. So basically, you know how many rows are going to be in your truth table. There's going to be 2 to the x rows in your truth table. So if you have less than 2 to the x conjunctions and more than 0, then it is a contingency. This corresponds to having some, but not all truth values in the final column of the truth table of the expression. If you try to bring it to full disjunctive normal form and it is a contradiction, then you won't end up with any conjunctions. So you will only end up with a false value. If you try to bring it to full disjunctive normal form and it's a tautology, you could end up with exactly 2 to the x. So first of all, you should try and make it true. And if you evaluate to true, you've proven it's a tautology. But if you end up with as many conjunctions as you have rows in your truth table, then that means every row in your truth table is true, right? So I can start with true, and then I can introduce variables using the the negation law. So I could say true is equal to a or not a, and then I can in each of these conjunctions I can introduce other variables by again doing and true. So I can start with just a true, and I can get back to full disjunctive normal form with as many conjunctions as I have rows in my truth table. But and if you do that, then you've shown that it's a tautology. All right, 736. So it was a bit of a speed run. Are there any other questions? It might be a lot to absorb, but so you'll have your the tutorial this week is the introduction tutorial. So this is how you submit your assignment and how to typeset using these sorts of expressions. And then next week is a bye week since Monday's a holiday. We will have no tutorial and no lecture, and then we'll come back the following week. Although do work on your assignment and do ask questions about it. So yeah, we've covered we've covered everything you need to do your assignment. But yeah, the only thing left is for you to, come to Discord, ask questions, get together with each other and discuss how you would approach these, et cetera, et cetera. Okay. So 7:37, but that's all the material I have for you tonight. Is it improper to use alternate parentheses to not confuse them? If you use alternate parentheses, please state, today have a tutorial. Today has the introductory tutorial. If you use alternate parentheses, please state some disclaimer at the top saying, I use these just to make things more clear. Just so that the TA knows. As long as, I mean, what we're most interested in is that you're clear in your communication. So if using alternate parentheses keeps it clear, just make sure you mention that you're using them. That's all. Yeah, and today's tutorial is the introductory tutorial. You have until next Sunday to do it, or this coming Sunday. How does the tutorial work? This first one is simply you're going to submit it like you would an assignment. So this is a practice for how to typeset your assignment. So that means you're going to practice how to make graphs, how to make truth tables, and how to express these mathematical symbols using Word or LaTeX or whatever you choose. So you're going to make up a document, you're going to convert it into a PDF, and you're going to upload it. In the tutorial section, there's an assignment, and so you're going to upload it to there before this Sunday at 11. And that's it. And there's no wrong answers. You just have to be able to do the formatting, right? So if you get it done and you submit it, then you get full marks. Right. Any other questions? Is there any specific format when using LaTeX, or more or less the same format as described in the tutorial video with Word? So I didn't have a chance to watch the tutorial video actually, but so with LaTeX, you can use a LaTeX editor. You can also enter LaTeX into Word when you do an insert equation. You can use LaTeX, and so I find LaTeX really nice because you don't have to click the menu. If you use a LaTeX editor, then you just use pure LaTeX, and you don't have to click the menu in order to make these complex mathematical expressions. You just use markup, right? You just use backslash something, and that's so backslash wedge is your logical and operator, and backslash v is your logical or operator. So that makes it really, really easy, but whatever works for you is fine, as long as your document is typeset. If you go further into math, you'll find that LaTeX. A lot of people prefer it to Word, but it does take there's a learning curve to it. It's difficult to pick up right away, but once you get used to it, it's easier, I find, and a lot of other people do. I don't know if does it complete this to unlock the assignments have marks? No, it's just well, it has marks in the sense that you can't submit anything until you complete it, but it has no marks on its own, no. But you have to, of course, agree to it to not commit any academic infractions. And then once you do that, you can unlock, you'll be able to access the assignments and then submit them. So it has no marks on its own, but okay. Any other questions? All right, I'm sticking around for a bit. So if you want to think about the lecture and then come back to me with questions, I'm going to stop the recording, but